Okay, today's topic is going to be combinational circuits, design methods, and arithmetic circuits. Basically, we're going to learn how to combine the basic logic gates that we've learned so far into doing specialized functions such as like adders, subtractors, decoders. And we'll talk about the ways that you can go about to create these specialized circuits. So we have two classes of logic circuits. One is the combinational. Essentially, all this means is that all the outputs depend entirely on immediately present inputs. There is a second one called sequential, and we won't cover this in the class. The only difference being that it depends on both present and past inputs, usually using a memory feedback loop here. So you can imagine in this black box you have inputs, outputs, and then somehow this memory of what happened comes back in as an input later. Given a combinational circuit, can you analyze its function? Of course, we can look at the circuit, derive an equation, and then we can start to draw a truth table. So we label inputs and outputs for this one, obtain the functions for the intermediate points, draw the truth table. We can see here by looking at this truth table, we're looking again at a XOR or a half adder circuit here, which of course is the one that does not have the carry in. It just produces a carry out and is a sum bit. So there are different methods. We can have gate level method with logic gates and the block level design method. Essentially, this is like when I would compare this to intro C as having like code that you keep rewriting all the time, or then you write a function, you keep calling it. Block level design, we can start to create these collections of logic circuits that perform a specialized function in a macro or a module and design circuits that way, so we can have some modularity. So the design method make use of logic gates, and this is essentially what happens when you buy integrated circuit IC chip. The design methods that we're going to go over actually go into the design of the actual chips you see in the marketplace. So there's 5 types of chips: SSI, MSI, LSI, VLSI, ULSI, all stand for the size of the integration. We typically deal with SSIs when doing things by hand, small scale integration, up to 12 gates. The main objective of circuit design is to reduce cost by reducing the number of gates or reducing IC packages for complex circuits, increasing speed and design simplicity. So if we're going to design an SSI using gate level design, build a half adder, well, we know how to draw a half adder, so we can start off with that. Draw the truth table as we did before, and then what we can do is obtain a simplified Boolean function and create the gates for that. So we draw the logic diagram. So we've created our half adder right here in this most simple format possible. So half adder adds up only 2 bits. To add 2 binary numbers, we need to add 3 bits, including the carry, because we can have a carry in and a carry out. And with the half adder, it only accounts for that carry out. So we need a full adder. So a full adder would take in a carry in, add that with the 2 digits we're looking to sum, and produce a carry out based on whether there was a carry in. So now it's a full adder. And essentially this can be created with 2 half adders and an OR gate, as we'll see later on here. So the full adder, as you can see, if the Z is 1, the sum is 1, this would be like a sum 1 plus 1 with a carry in of 1 is essentially how to think about that. Or a carry in of 1 would just yield a sum of 1. So you can see how this will add binary numbers. So using a K-map, we simplify this full adder to the following equation. Also, you could have done this using algebraic manipulation. Here's the rundown for that. The circuit for the formula, as I said, is generally a 2 half adders connected by an OR gate here. Mainly what you see here is the carry in or carry out being used as an input on the second level of the adder. So you can see full adder made from 2 half adders plus an OR gate. So there's our half adder circuits here, and there's the OR gate down here. So code converters, this is another type of combinational circuit here. Take an input code and translate it to an equivalent output code, like gray code, or say 1's complement, 2's complement. We're going to use, in this example, XS3 code, which essentially adds 3 to a number. So you have your inputs for A, B, C, D. We'll add 3 to it. So if your input was 0, your output would be 0, 0, 1, 1. Or if we think about these in decimal, input of 0, output of 3. Input of 1, output of 4. Input of 2, output of 5, etc., etc., etc. At this point, these X's don't matter anymore because we don't have enough bits to actually represent the next number. This would be so those are considered empties. So what they did here for this method was, you can see they divided each output into a separate equation and did K-map simplification for each output bit, which is essential for solving this problem here. You can see the finalized equation here, W equals X equals Y equals Z equals. We won't go into detail on there, but the Carnot simplification we talked about in the last lecture should make that clear. So the block level design method is another way. So more complex circuits can be built using block level method, and this is where we get to use the modularity and the repeating. Like I said, the best way to think about that is a function in C++. So as opposed to gate level design, we use algorithms or formula to derive the circuit, usually by breaking the problem down. So we'll start by looking at a 4-bit parallel adder and also known as a ripple adder. We'll start by looking at that. So consider a circuit to add 2 4-bit numbers together in a carry-in to produce a 5-bit result. 5 bits is sufficient because the largest result with 5 bits would be 1 1 1 1 1. How would you actually create this adder? Well, if we use the SSI method that we talked about earlier, where you generate the truth table and then simplify the equations using K-map or Boolean simplification, you get a big problem already because there's 2 to the 9. That's 512 entries in the truth table. So you'd get this question wrong on a test if you try doing it this way. So you have to use the alternative design, where we can look at the carry out of index plus 1 for some index plus 1 equals x sub I plus y sub I plus c sub I. So if you can't visualize this, you'll see in the next slide here what's going on. Essentially what this is, it creates a full adder, but since we're dealing with more than 2 bits, we can string them together, is essentially what this formula is saying here. So I have cascading 4 full adders via their carries, so we have 4 full adders, and you'll see here that their outputs are all tailored together here. We have the carry out of for the 4th most significant bit, and then all the way down to the least significant bit here. And you'll see that our result would actually wind up with a 5-bit number. Green characters here meaning outputs, blue ones meaning inputs. You can see here we get this 5 result adding 2 4-bit numbers, which is okay because the largest that you could get adding 2 4-bit numbers would be a 5-bit number. So note that the carry propagated by cascading the carry from one full adder to the next. It's called a parallel adder, also called a ripple adder. So you can see here that although these inputs all come in at the Y4, X4, this carry 4 depends on the previous input here. So you can see these carries are sort of rippling like a wave down the adder. You can see here this input depends on this input, depends on this input, depends on this input. So it's like a wave, it's rippling. And there's some cons to that effect. So going back to the XS3 code converter, using this new method here, gate level design can be used since there's only four inputs. However, there is alternate design. So we look at the actual problem and we say, well, BCD code to XS3 code equals the BCD code plus 3 in binary, essentially. So the block level circuit here would look something like this. You have a 4-bit parallel adder that always adds 3 down here. So you have an input here, always have 3 here, so this always adds 3, so the output of your 4-bit parallel ripple adder would give you XS3 code in this example. So larger parallel adders can be built from smaller ones. For example, to create a 16-bit parallel adder, we could use 4 4-bit parallel adders or 8 2-bit parallel adders. You know, however you wanted to do it. We'll see that there's a formula for that. Shortened notation for multiple lines is just FYI here. To have this particular notation here, the line drawn through it with a 4 means there are 4 arrows, and we're going to go from S4 decrementing down to S1. You'll see here S4, S3, S2, S1. Just the shorthand notation here. Important to note that ripple carry circuits are slow because of long delays needed to propagate the carries. We spoke about, but we didn't get in focus on. We won't really go into too much detail on that today. The time delays when you have propagation of bits through logic gates, and the problem with that ripple is that you're introducing so many tiers for each bit. There's always an extra tier, so it actually slows down the addition process. Here's a 4-bit parallel adder with subtractor. Recall that subtraction is performed essentially by doing addition of a 2's complement number. So if I add the 2's complement of a number, so say I want 5 minus 4, I would take 5, I get the 2's complement of 4, I would add them together, and the result would be 1. So we use that fact. There's no such thing as like building a subtractor. It's built using an adder. The only difference being that we need to get it to 2's complement form before we put it as an input into the adder. So the way this is done, they use a control signal. S equals 0 means add, S equals 1 means subtract. There's some Boolean algebra here to show what should happen here. X minus y equals x plus negative y. X plus 2's complement of y equals x plus 1 complement of y plus 1. Therefore, x plus 1 equals x plus 1. So x minus y does equal x plus negative y. So we have our method here. Using an XOR gate with the signal, we have, you can see here that with the XOR, when s equals 0, the output here would be y, and when it equals 1, it's going to be y bar. And s will be connected to the carry in, as we'll see here. So to turn our adder into a subtractor, essentially what this does is if we want to subtract, we turn this on and basically take the 1's complement of y before we put it in here using the following method. If s equals 0, then x plus y appears as the result, so it won't change this. So depending on whether this s is 1 or 0, depends on whether this gets changed to 2's complement, depends on whether this adds or subtracts the 2 numbers. Really, it always adds. It's just adding a negative number, if you want to think about it like that. So here's our half adder from earlier, and we can see how this is just showing a reduction of the original, showing the logic gates as we begin to reduce the equation here. So you'll see here's the equation. We've seen this example many times already, and you can just see here how the gates are actually decreasing as we go further along in the simplification. So with the full adder, we'll see the same thing here down to the simplification. Here we see they're constructing this using the here's the SSI method here. Moving forward in the parallel adder, we can see that they're using our the parallel adder by successfully daisy chaining the 4 full adders together. So you could do this in 2 ways with the 4-bit number. You could actually have the serial, which is 1 full adder that handles 4 bits, or you can just parallel. So NFA is for in bits. So if we needed 8 bits, we could use 4 2-bit full adders, etc. Any combination that would get you to the end result here. So we can see the cascading adder, and here's with the shorthand notation we talked about earlier. You can extend this for large numbers. So here we have a 16-bit adder here, represented as a with the symbolic representation here for the adder. So you can see here this can be used to make a 6-person voting system using two adders that sum up to three votes at a time. These add up here. So we have a full adder here that can add up to 3, another one here that adds up to 3, and then you can see this gets the final count. Summary, using the subtractor, basically all we're doing is taking the 2's complement before adding. I'm not going to go into too much detail on this, but we'll discuss this briefly. The comparator for an arithmetic circuit. How would you compare whether a number A is greater than B? Well, the easy way to think about that is if one of the most significant bits, like if you have 4 bits, if bit 3 is higher than in one than the other, like if it's 1 and the other one's 0, you know that that number is greater. So essentially what we can do is start looking from left to right and wait until we find that discrepancy and determine whether or not. And if it goes all the way through, we know that they're equal, and we can negate that and determine whether or not it's less than. So using, for equality comparator, you generally just use the XNOR here. This will return true if both of the inputs are exactly the same. So we can see how you can determine equality across 2 numbers utilizing this in a daisy chain fashion. And that's just, essentially what this does here. To get a little bit more complicated, I reset the, find where we were in the slides. Hold on just a sec. There we go. So you can see the equality comparator, and of course this gets a little bit more complex as we look at the less than and greater than as well. So how can we find A greater than B? Truth table would have a lot of rows, 2 to the 8, 256 rows in here. So we don't want to use that. We don't want to use the SSI method here. So we can see here that A is greater than B for one reason here. This bit's high and this one is low. That's it. With that piece of information, we already know that that number is greater than. So this is going to go through and show you that because A3 and not B3 equals 1. So they're starting to build the equation here, essentially. Then we go to the second tier, and we can see that in the second digit, it depends on C3 as well, being ORed with A2 and not B2. So not to go into too much detail on the construction of this, we can get all the way to the end here. Once the actual formula has been derived, and this is for greater than, you can actually build the whether it's greater than circuit here, and using a similar method we can find less than, which is essentially just the opposite there. So now you have a full comparator circuit here. You can see this is a little bit complex, but when you look at the actual equations that you use to deduce this, you see that it is algorithmic. It actually follows a trail on the road there. So here would be our block diagram for a 4-bit comparator. Definitely not as beastly looking as the actual logic circuit for it. Calculation of circuit delays, we're going to rush through this. Given a logic gate with delay, we can see that there is, the more gates you introduce to a circuit, the longer the delay you can expect if it has to travel through all of those gates to lead to your output. So one of the thing we've looked at today is the ripple adder. And it's like, how could you fix the delays there in the ripple adder? And the way they do this, and you can see here, if you want to go into more detail and look at this slides later, you can. This is actually showing what happens on each tier here in that ripple to the time propagation delay here. So the propagation delay of a ripple carrier is proportional to the number of bits it handles, and the maximum delay being number of bits minus 1 times 2 plus 3 to the t, or times t. So this gets worse and worse the more bits you add. It's the propagation. So the way this was fixed, there's a couple strategies you can employ. Is use ECL rather than TTL, simply because ECL is faster. And then your only limitation is speed of light. Or use gate level design, but you can get complicated designs for large circuits. And product sometimes you may have a whole ton of inputs when you actually wind up with the final solution. So what they did here was someone created a clever algorithm here for this particular problem, the look-ahead carry adder. Essentially, when we look at the actual full adder, if you were to tap this line here and this one here, you can see whether a carry needs to be propagated, as in moved along, or whether one needs to be generated here. Now, knowing that information beforehand, you can tailor a circuit based on this principle. And you can see that the I plus 1 level starts here, I plus 2 level here, I plus 3, and we start to see the algorithm right here. You can see it's essentially just increasing the index by 1. So what this does is it flattens the formula for the carries by using this look-ahead method. It actually knows whether it needs to propagate or generate early on based on what previous bits have done. Similar to parallel processing, if you want to think about it like that. So with higher, the more carries, the longer and longer this formula will actually get, because Ci plus 3, as we see here, well, even just looking at Ci plus 2, it contains all of this here. So when we replace that in an equation, you'll see this keeps on growing each time. We won't go into full detail on that in this course. So this is what an actual look-ahead carry adder looks like, and is really probably see more of this in computer architecture. You'll do the look-ahead stuff, and you can see here that this thing is going to add a lot faster than a ripple carrier. This one, because just based on that fact that it can tell whether it needs to propagate immediately upon the inputs, when it's calculating bit for bit what's going to happen to the next bit. So this is just another pictorial representation. That's going to end what we're doing today, and the lab today is going to be pretty long, so I kind of flew through the lecture. A lot of that is a lot more detail than what we're going to go into in the actual course, but felt it all needed to be said.